Okay, we're ready. Welcome back. One more week of suffering. I just want to remind you that this set of homework problems are due next Monday until 11:59. Don't forget to silence your microphone, please, and turn your webcam off. I want to double check. Can you hear me? Anybody said yes or no?
Yes.
Okay, yeah, okay, but turn now turn your microphone off. All right, this week we're gonna do deflection. I just want you to understand and remember that all the time, whenever we're talking about deflection, the EI, the model elasticity and the moment inertia, they're always going to be at the bottom of whatever formula or equation we have. Always gonna be the EI. And the EI is also known, as the flexural stiffness. So whatever we do, also it has to be in inches. The answer is going to be in inches because the modulus of elasticity is in KSI, moment inertia inches to the fourth, and L is in feet multiplied times 12. So always it's going to be in inch. The other day, I went over this and I put it again to show you. This is page 2 of the notes that I put in Blackboard. Whenever we're doing deflection, we look at the elastic curve, how the beam or how the frame is going to deform on footing. And obviously, this is a fixed support, so there's no movement in here. There is a roller, it will not move up or down, but there is a rotation. Whenever we had a moment, I want to point out that this is the deflected shape, but since there's no load in here, this remains straight. There's curvature all over for this elastic curve, but in here, it's just a straight line. Whenever we had a hinge, like in this case, at this location, a location of the hinge, obviously the hinge is going to go down, and there are going to be two different angles coming from the left or coming from the right. And in here we had the deflected shape. Whenever we had a continuous beam, even though that we have only load in here, all the members you will see in a couple of weeks that all of them help resisting the load. That's why we had a elastic curve that had a curvature. By the end of the semester, we're going to be looking at frames. And no matter what we do, this rigid joint remain 90 degrees. This remain 90 degrees, and the whole frame is moving to the right. The same happen with, they have two base both of them move to the right, and this remains an identity. Whenever we have symmetry with both the geometry and the loading, you're gonna see that we don't have this lateral movement. The joint remained at the location where they started because of both. And you have to remember symmetry with the geometry and symmetry with the load. Some of you told me the other day that you were familiar with the moment area. And the reason why I'm going to cover the moment area is because we need to know the moment area in order to understand what we're going to do later, this virtual work on energy method. So whenever we had the moment area theorem, there are two of them. The load, they're showing any shape for the load. But what is important that the moment diagram, this load is producing certain moment diagram. The moment area theorem, as you already know from previous semester, uses the moment diagram divided by this structure stiffness that I mentioned before. The shape of the moment diagram is divided by EI. And there are two theorems. And the first one is very simple. This is page 4 of what I'm giving to you. I'm going to increase the size so you can see the first one. The first one says that the change in a slope between any 2 points on the elastic curve equals the area under the M over EI diagram between these 2 points. Saying that the change in a slope is equal to the area under the M over EI diagram, this area. And this is what is shown in here. This is the elastic curve. This is what I was talking about before. This is the elastic curve. This is a point on the elastic curve, and this is the tangent. This is a straight line. This is another point in the elastic curve, another tangent. This is a straight line. And they're saying that for this line to become this, it had to rotate this amount. So for this line, A, to become B, it had to rotate it. And they call it theta BA. This theta BA is equal to the area under the M over EI diagram. So changing slope are equal to areas under the M over EI diagram. So this change in slope is equal to area. The second theorem is a little bit more complicated. It says that the vertical deviation of the tangent at the point A on the elastic curve with respect to a tangent extended from another point B. What I'm saying in here is, look, this is the elastic curve. This is tangent A, this is tangent B. They're talking about the distance from this tangent, from this line to the elastic curve is called T from letter T from A to B. The distance from this tangent to the elastic curve at point B, this distance here is called T from B to A. And this is the tangential deviation. And the tangential deviation, and here they're saying is equal to the moment of the area under the M over EI diagram. So the moment of the area under the M over EI diagram between the 2 points, point A and B, and the moment is computed about the point A, the point on the elastic curve where the deviation TAB is to be determined. So what they're saying in there is that if you want to find this distance, you need to apply moment about point A. If you want to find this distance, you need to apply moment about B. And this is what I'm going to show to you with an example. This is the easiest of all the problems. And most of the time, you're going to find that EI is constant. Look, this value of constant, we had a beam with a load in the middle, L over 2, L over 2. So the reaction here is going to be P over 2, P over 2. This is the elastic curve. what I have in here, this is the elastic curve. It means how this beam will deform when you apply the load. And from the original location of the beam to the final location, this is the deflection. From here to here, deflection. All of these values, they are deflection. Here at A, this is the tangent at here at point A on the elastic curve. I had this tangent, and this is what we call the slope or the rotation. At A, always go from the horizontal to the tangent, theta A. I have another tangent here to C. So this tangent to point C from the original location of the beam to the tangent, the theta C. And like I said, this is the elastic curve. So the sign convention that we use in here is that a counterclockwise, a rotation that goes in this direction is positive. So counterclockwise is positive. So just anybody in the class, I want you to write, look, this rotation going from the horizontal to the tangent is positive or negative? This is considered positive. So what is this? Negative. And this one, from the horizontal to the tangent, counterclockwise, positive. That's the sign convention that I'm going to use in a little while. And this is the problem. This is a simple beam. I was saying that the load is in the middle. So this reaction, P over 2 because of symmetry. This force times this distance, P over 2 times L over 2, P over 4, that is the moment. And this, of course, the moment diagram is formed by a straight line. So you have to divide every single value of the moment by a constant EI. The shape is exactly the same. Since EI is constant, the shape or the new diagram, this is the M over EI diagram. The shape of this diagram is exactly the same as the shape of the typical moment diagram divided by EI. This is the deflected shape. What I have in here is my elastic curve. This in here is my elastic curve. Point A doesn't move, only rotates. Point C doesn't move. This deflects down. So all of these are deflections. So this is the elastic curve. I have put a tangent to point A. This is a straight line, a tangent to this point. I have put another tangent to point C, also a straight line. So this theta CA, they change the slope between these two lines because from this line, if I rotate this amount about this point, I get this tangent. So this theta CA is equal to the area under the M over EI diagram between A and C. This is point A and this is point C. So this angle, theta CA, is equal to all of this area. And remember, to theta A, I need to add this angle, get to the next slope. So what I have in here, next, look, this area is 1/2 of L times PL over 4 EI. And to compute TCA, point C on the elastic curve, to tangent to elastic curve to point C. Look, this is point A. Point A, this is a tangent, and the distance from point C to the tangent is called TCA. And this is measured perpendicular to the original location of the elastic curve. So perpendicular, this line is perpendicular to that, TCA. So this is going to be equal to the moment of the area between A and C. Look, area A and C, all of this area. The moment about point C. So this distance TCA is equal to the moment of the area between A and C. This is A and C, A and C. The moment of all of this area about point C. The distance from the centroid of this area to point C, all this distance is L over 2. So this distance from the centroid to this point is L over 2. So I'm going to compute TCA. It's going to be this area under the M over EI diagram. This area is 1/2 of L times P over 4 EI multiplied times L over 2. I'm going to compute theta A. To compute theta A, I'm going to find TCA first. And I was saying the total area, 1/2 PL over 4EI times L. The distance to the central, L over 2. So this gives me PL cube over 16 EI. This is the area under the M over EI diagram between point A and C. 1/2 PL over 4EI times L over 2. This area, 1/2 of L times P over 4EI, and the distance from here to here is L over 2. That gives me TCA. I'm going to divide TCA by this length. It's going to give me the tangent of this angle. Since that angle is very small, the tangent and the angle there are exactly the same. So this is what I'm doing in here. This TCA, whenever this value is below the elastic curve, is positive. Look. This is the elastic curve. And this TCA is below the elastic curve, is a positive value. And that's why, based on the area, positive area times the distance, positive area, it means that it is below the elastic curve. So theta A, the tangent of theta A is almost the angle, TCA over L, PL cubed over 16 EI divided by L. So theta A is PL squared over 16 EI in this direction. So this angle, clockwise, theta A is computed in here. The tangent, TCA over L, PL cubed over 16 EI over L is PL squared over 16 EI. This direction is positive or negative? Anybody? This direction?
Negative.
Negative. Excellent. So I'm going to compute now theta CA. I'm going to compute theta CA. Going back to this. I'm going to compute this. And this angle is equal to the area under the M over EI diagram. This area under the M over EI diagram between point A and point C. A and C. So it's all of this area is equal to this angle. So down below here, equal to the area under MRI diagram between point A and C, the total area is 1/2 of PL over 40I times L, PL squared over 8EI. We're talking about this area. To compute theta C, I'm going to have theta A plus theta CA is going to give me this angle. So theta A plus theta CA is going to give me this angle. And this is the equation that I have in here. Theta A plus the change in slope between the two tangents, theta CA, gave me the next angle, theta C. Again, this angle plus the change in slope gave me the next one. Theta A, we computed in the previous page, and I asked you, you said a negative. Theta CA, we just computed PL squared over A. So theta A plus theta CA give me theta C. So theta C is PL squared over 16E. This is the value that I compute. This is theta C. And it can positive. You can see this went with a negative. We check this. This is a positive area. And this can positive. So it means that this rotation is in this direction as indicated in here. That's the direction of the rotation. So theta C is PL squared over 16. I'm going to compute the deflection. So I already computed theta A, I computed theta C. I'm going to compute the deflection. I'm going to compute this by. To compute the deflection in this method, we use tangent. So I'm going to put a tangent through this point. And the tangent to this point is horizontal line. Because this is exactly because of symmetry. This is going to be exactly a horizontal line. And the horizontal line, the deflection, because this line and this line, this deflection at B is also equal to this distance, is also equal to that distance. This is a distance from a point on the elastic curve to the tangent. That's why I call it T from A to B. This in here, because of symmetry, is the same as this, the same as that. Point on the elastic curve, C2, a tangent to point B, that's what I call TCB. This is going to be equal to the moment of the area under the M over EI diagram between A and B. The area, the moment of the area and the M over EI diagram between A and B about point A. So this is the area. Under the M over EI diagram between point A and point B. This is the area between A and B. I need to apply the moment about A because I'm measuring my tangential deviation from point A. I measure from here to the tangent, moment about A. So the centroid, because this is 1/2 of L, and this is the centroid. This distance is 2/3 of L over 2. So what I done here, I want to compute the deflection at B. I have shown to you it's equal to TAB or TCB delta B. And so it's going to be the first moment of the area between A and B about A. Look, 1/2 P over 4EI, only L over 2. This area in here, 1/2 P over 4EI times L over 2. Multiply times this distance. Multiply times 2/3 L over 2. It gave you a deflection P cubed over 4EI going down. Every single textbook has a table for deflection and rotation. This is the case that I just did. When the load is exactly in the middle. The maximum deflection at the middle PL cubed over 48. Yeah. The theta at x equal to 0 here, or x equal to L, this is PL squared over 16 EI. This is what I found before. This is exactly what I found before. So the reason why I'm showing this to you is because it's very important to understand what I'm going to do next. That is one of the easiest methods to compute deflection and rotation or slope, not only for beams, especially for frames. But I want you to remember that the change in the slopes is equal to areas under the M over EI diagram. So the change in slope areas under the M over EI diagram. What we're going to do next this is on page 13. And the method is called virtual work. It's an energy method, but also is known as the unit load method because we're going to be placing unit loads allocation whenever we have to compute deflection. We're going to be putting unit moments at the location whenever we want to compute rotation. But it's also called the dummy load because we put in a fictitious load at certain locations. So all of these are energy methods known as virtual work, unit load, or dummy load. From our textbook, I have put this. And what it is that whenever I'm in class and I show you this, look, I deflected, I unloaded, look, everything is elastic. So whenever I'm doing this, there is a rotation. Whenever I'm doing this, there is a rotation, the cross section. Remember from mechanical solid, plane section before bending remain plane after bending. It means that the cross section of the structure is rotating as a rigid body. So plane section before bending remain plane after bending is rotating as a rigid body. Whenever we're doing this rotation, the cross section, the moment is rotating the cross section, and the rotation is going through an angle. You can see that it's perfectly vertical. I'm rotating, so I'm creating an angle. So the internal work is going to be the moment and the rotation. Externally, the work is the force times the distance. So whenever we had a load and created deflection, the force is going to move to that deflection. So the external work is the force times the distance traveled by the force. So this vector work is very simple. And I want to point out, it's the best that we have for beams and frame. And it consists in finding, if you want to find the deflection of point A, you want to find this deflection, you put a unit load in the direction of the deflection. If you believe that this point is going to go down, you put this force going down. If you believe for any reason that the deflection is going to go up, you put this up. If it becomes positive, as assumed negative, the opposite direction. So this is the unit load that is placed at this location. This unit load at this section, we had a shear force, we had a bending moment. What I want to point out, this is the dummy load, and this is the moment produced by the dummy load. Always, it's gonna be called letter M. So the small m, that's the moment produced by the unit load or by the unit moment. Right now, we're talking only about a unit load. So this unit load goes with the letter M moment. They represent the load by something that is not uniform. It doesn't matter at this time. But what is important is that point A, due to this load, this point A moves the distance delta. So if they take the free body of this location at X, the same as the other one, we had a shear force and a moment produced by the load is called the large M. And this is the slope, the changing slope, the angle. This is equal to the area under the M over EI diagonal. So the area under M over EI diagram is going to be M over EI times the letter dx. So the formula for the deflection, this in here is the external work. See, there is a conservation of energy because everything is on the elastic range. Like I was saying, I deflect this, go back. I deflect this, go back. No permanent deformation. So this is the external work. This is the internal work. We had mdx, area under the M over EI diagram, the rotation, the moment times the rotation, integration over the length. Normally, when we had this formula, we never write the one again. And if you forget about this one and you look at the delta, you're going to see that the unit, they don't match. They do not match because this is in keep. We never write it because one time delta is always delta. So this is what we're going to use. We're going to find the moment produced by the load, the moment produced by the dummy load, and we're going to find integration over the length. In order to understand this, first, I want you to look at it. I had a terminal structure. The distance between this reaction and this load is 10 from this load and the reaction is 10, and between the reaction and this is. So the moment diagram is going to have a straight line between this point and that point. You have a straight line between the load and the support and another straight. Obviously, there are three equations. There are three equations to describe the change in the moment diagram. We have three equations. Look, this is equation I'm calling equation 1. This is equation 2, and this is equation 3. This equation is only good between this point and this point because to the right, a different equation. This equation is good between this point and this point. This equation only good between this point and this point. And the third equation is good between this point and this point. So the rule is as follows. Between any two loads, and the reactions are also considered loads. Between any two loads, there is a different equation. Between any two loads, there is a different equation. With any two loads, there's a different equation. So for the virtual work method, we have to write equation for the moment, for the given loading and for the dummy load. However, look, if I put my origin at this location, somebody write please. This equation, the limit for this equation, just write in there, the limit is from which value to what value if I put the origin at this location. 0 and 10, exactly, good. If I leave the origin at this location, this second equation, if I leave the origin at this location, this second equation is valid between what point and what value? This second equation, if I leave x at that location, 10 to 20, 10 and 20, x. What about the last equation? If I leave my origin at this location, the last equation is good between, right? This last equation is good between 20 and 30. Exactly. So for this method, it's very important the location of the origin. If we want to do integration, we prefer to go from 0 to certain value. We don't want to go from 0 to 10 and then from 10 to 20 after that 20 to 30. So what do? We move the origin to a convenient location. For instance, to describe equation number 1, I'm gonna leave the origin at this location. And I'm gonna put a section in here. I'm gonna call this section 1, 1. So for equation number 1, I'm gonna leave the origin in here. I'm gonna put section. For equation number 2, I'm gonna put a typical section in there. But I'm gonna move my origin to this location. So I'm moving the origin to this location. So now, when I look at this equation is the origin is at this location. It's good between which value and what value. If I move the origin now for this equation, I put the origin at this location. So somebody write from where to where. If I put the origin at this location, this second equation now is good between this point and this point. So between what and what? 0 to 10. 0 to 10. But my free body is going to be all of this. I want you to be very careful and look. My free body is all of this. Because if I put only this portion, I forget that there is a moment produced by this force. So whenever I take this, section 2, go from 0 to 10, all of this is my free body. When I do section 1, only this is my free body. For the next equation, I'm going to put section 3, my origin in here. So for section 3.3, I have moved the origin to this location. Now, this equation is only good between this point and this point. What are the values? From where to where? From this point to this point. Limit from where to where? This equation is good between this point and this point. From 0 to 10. Excellent. 0 to 10. So you do have to remember, always move your origin to a convenient location. And this is my free body for that. So always remember, between any two loads, there is a different equation. In this case, 3. The origin, we want to move it to convenient locations to have from 0 to certain value, from 0 to certain values. I need 3 sections, 1, 2, and 3, because I had 3 equations. If I have 4 equations, I need 4 sections. This is my free body for section 1. All of this, my free body for section 2, and all of this, my free body for section 3. Section 1 between 0 and 10. Section 2 also between 0 and 10. Section 3 between 0 and 10. For section 2, the limit is between 0 and 10. However, I have to use all of this in my free body for section 2. Did I answer your question? Section 2 between 0 and 10? Any other question? Because I'm going to move to an example. Any other question? Okay, Miguel. This is page 16. Here, they want to find the vertical deflection of point C, the deflection of this point. The moment inertia given at 53.8 inches to the 4. The modulus elasticity, 29,000 KSI. KSI. This is the given load. Only A kit. I have computed the reaction for you because 8 times 5 is 40 and 4 times 10 is 40. So in theory, how many equations do I have that describe the moment for this beam? How many equations do I have? In theory, 3. Between this low and this low, 1 section. Between this low and this low, 1 section. Between this low and the end, 3 sections. Since I want to compute the vertical deflection of point C, the dummy load, I put a unit load at C because they want me to compute the vertical deflection of point C. I have computed the reaction. Look, 1 times 5 is 5.5 times 10 is 5, 1 and 0.5, 1.5, 1.5. How many equations in theory do I have in here? How many equations? Between the loads, how many? For the dummy, in theory, how many equations do I have to describe the moment? Also 3. 1, 2, 3. However, what is the moment produced by all of these loads between B and C? What is the moment? Anybody? Wait, I'm going to answer your question about why I put a Z. What is the moment in here? The magnitude of the moment. See, we don't have any load in here. No moment. There's no moment in here because there's no load. There's no moment. But let me answer why I place the unit load at C. Look. The question for this problem is to compute the vertical deflection at C. So I had to put a unit load at C, and that's why I put my unit load at C. I had created a new beam. A new beam that is what I had before, only with a load at C. So you place a unit vertical load allocation where the deflection is to be. I asked you, and correctly, you said, I had 3 sections, I need this section, I need this section, I need this section. I have moved the origin, section 1, and we always go from the origin to the section. Section 1. I had created section 2. I put the origin at this location. I go from the origin to section. I created section 3 from the origin to the section. So we always, and this seems to be very simple, but this is a point where people make mistakes. We always go from the origin to the section, from the origin to the section, from the origin to the section. And for the dummy load, I had to use the same section. Look, section 3.3, the same origin. Section 2.2, the same origin. Section 1.1, the same origin. Any question about the location of the section, location of the origin? Okay. So I'm going to take section 1 for both of them. So I'm going to draw this section. I'm going to draw this section. Once you get experience, you know that the moment about this point is A times X. You know the moment at this point is 0. But I'm going to do it because the first day, I'll take this free body and this free body. And this is exactly what I have in here. I have put section 1.1, X between 0 and 5. 5, 10, and 5. So section 1.1. X between 0 and 5 for both. This is for the given loading. I had A, this is my section. This section, I got it from here. So this section has the load, the origin, and nothing else. This is the moment the uppercase, the large M, is the one produced by the loading, and is A times X. Now, look, I have a mistake in here. What is the sign? M is equal to positive AX, or it's going to be negative AX? Look, AX plus M equal to 0. So M is going to be equal to negative. So here, I have to put a negative value. This is for the dummy load. This is the same location. This is the same location. something that I want you to remember, that I had to assume the large M and the little m going in the same direction, both of them counterclockwise or both of them clockwise. That means the sign convention. But for the dummy load, look, there is nothing here. So this M is zero. Down below in here, I have multiplied large M and little m, give me zero. So this formula is gonna have, this is gonna be the summation of all integration over the length, the dummy moment, the given load moment. If this is zero, it will kill this portion. That's why in here, section 1.1, we don't have to use it because now the moment is zero. Whenever you look at this section, we know that the moment is AX and there's no moment, so this will kill this. Having done this, section 3.3, and this is for the given loading. Section 3.3 in here. What is the large M? What is the large M in here? What is the large M if I use it? Zero. And what is the little m in here? What is the little m in here? 1 times x. X times 0, it kills it. So the only section that I have to use, the only really section that I have to use for this problem is section 2.2. Because there is a moment due to the given load, there is a moment due to the dummy load. So this problem, this section is gone because 0 times AX. This section is gone because 0 times X. So I only need section 2.2. Section 2.2 go between 0 and this point, between A and B. So this is going to be good between 0 and 10. I want you to look at section 2.2. Section 2.2, good between 0 and 10. This is the free body to the left. He had the 8 kips, he had the 5. So this is a given distance. He had the reaction, and he had this X. Section 2.2, I assume M going in the counterclockwise direction. Section 2.2 for the dummy load, I had a 0.5. I assume I had the origin. I assume little m had to be in the same direction because that means using the same sign convention. One more time, what I have in there, section 2.2, is this one. We have to use everything to the left. Otherwise, we change the problem because this A is producing a moment. We have to use everything to the left. Everything. You have the 8, the 12, you have the 0.5, and nothing else. This free body I'm applying moment about 2, summation moment about 2, give me, look, A times 5 plus X minus 12 and X plus M equal to 0. The M equation, 4X minus 40. For the dummy load, moment about the same section, could you also solve for the right? Section 2. Good question. For section 2, the question is, can I use this? Certainly. I need to put the origin at this location, also do between 0 and 10. I need to put the origin at this location, also between 0 and 10. So it makes no difference. Sometimes, based on the number of forces that you have on one side, it does make difference. But remember, the moment coming from the left is equal and opposite to the moment coming from the right. So I can take this section or I can take this section. To answer your question, if I take this side, I have to put the origin at this location. I have to put the origin at this. Does that answer your question? Any more questions? So, section 2, one more time, I want to emphasize that we had to use everything to the left for the section. The 8, the 5, the 12, and here everything to the left of the section. This gave me a moment 4x minus 4. This one in here, we have 0.5x plus m, give me a minus 0.5x. I have done section 3 just for today. In the future, I will not mess with this section because, like I said, section 3, the moment is 0, this moment is minus x. So 0 times x is all, it goes away. So the deflection was at C. Remember that we had a 1 in here that we don't put. We just only use the delta. Summation of the integration over the length of all the section moment produced by the given loading and the moment produced by the dummy loading over EI. We only had one because section 1 and section 3, 0. We only had section 2. From 0 to, this is the moment that I found in the previous page. This is the moment I found in the previous page, large M, little m, dx over EI. One more time. This is what I found in the previous page. Remember, M due to the given load, M due to the dummy load. So this in here. This in here gives me M times little m dx over EI. It comes at minus 2x cubed over 3EI. This integration and plus 20x squared over 2EI from between 0 and 10. So the integration gives you 333.33 over EI. Whenever we had the deflection, we're going to multiply this times 12 cubed. Whenever we know more elasticity, 29,000, we're going to put it in here. Whenever we know I is always inches to the 4 here, so they give us 0.37. It came positive, means as assumed. We assume the dummy load going down, means as assumed. So, any questions about this? Any question about this problem? If the value E and I, why 12? Because look, this is what we have, the original equation. This is in kip, this is inches. We come here and we have the moment is kip foot, the little moment is kip foot, dx is in foot, this is kip inch square, this is inches to the 4. Right? So in here I have 12, I have 12, I have 12. The kip on the top with the kip on the bottom, it goes. Inch to the 4 inch square, so it becomes square. Right? So I had another kip in here with this kip, it goes. So 12, 12, 12, and we had inch square, so goes. So we had, look, 12, 12, 12. We had in here inches square, so this become inch, this goes, and the answer is an inch. So whenever we have a deflection, we're going to multiply this times 12 to the cube. I was saying that if EI is not given, you're going to leave the answer in terms of EI. You do not have to multiply it times 12 to the cube. If EI is given as you're welcome, as constant, you leave the answer like this. You do not multiply times 12. Any other question? Now we're going to change the problem. We still have some time. Look, this is the same problem. Whenever we had the same problem and the value for something different, now they're asking for the slope at P that is also known as the rotation at P. This is like the previous problem. Theta B is the slope, or also known as the rotation. This is the same problem. So we have 1, 2, 3. In order to find rotation, we're going to put a unit moment. Whenever we compute deflection, we put a unit load. Just to give you an idea. This is the way when you push in here, this is the elastic curve. This is what I was mentioning before. What I mentioned, elastic curve. Elastic curve show the deformed shape of the structure. This is pushing down, that goes up, and this is straight. There's no load, there's a straight line. But look, this means that the slope from the horizontal to the tangent, the slope is clockwise. Sometimes it's impossible. Sometimes it's impossible to determine if it's clockwise or counterclockwise. Counterclockwise or clockwise, sometimes it's extremely difficult. But so what I'm going to do in here, since they want me to find this value, I'm going to put a unit moment in that direction. And this is what I have in here. This is page 17. This is the given loading, the same as before. So we already had the equation in here. There's an equation in here, 8x. We had equation here, this is still 0. This is my dummy loading now. Dummy because it's not a given loading. Look, I put the unit moment in the same direction where I believe. The same direction, look, this is gonna go in a clockwise direction. So I'm putting this moment in the clockwise. If I assume any direction, it can positive, assume negative, I have to remove. I have to use the same section, 1, 2, and 3. To compute the reaction, I apply moment about this point, I came 1/10, 1/10. Every time that you have a unit moment, this reaction will be 1 over this span. You can compute a reaction. This is simple. Only one known moment in here going in this direction. This moment has to be in the opposite, this time this, opposite direction to put an equilibrium. I apply moment about point A. You can see By times 10 minus 1 equal to 0. By is 1/10. Summation of forces in Y, 1/10. Always. Why didn't you put the dummy load at B? Okay. Remember that now the dummy load is a moment. They want you to find the slope at B. Before was the deflection. The deflection at C, we put a unit load. Deflection go with unit load. Rotation go with unit moment. So my dummy load at B now is a moment. So now my dummy, because they want a slope, I put a moment. If I want deflection, I put a load. So I'm putting, you question, why didn't you put the dummy load at B? I'm putting the dummy moment. Did I clarify that or did you? Did I clarify that or you need more? So, yes, okay. So the dummy for rotation is a dummy moment. Those are the location and the direction that we believe. So look, the origin before was at this location. The origin for section 1 was at this location. What is the moment? Look at this. If I put my origin at this location, I'm gonna put it in, just leave it at that. If I put my origin in here, what is the letter M in here? Anyway, 0. So it killed the A times X. There's no moment in here. What about this section? If I put my origin here, is there a moment here? Look, we go. Anyway, if I put the origin here, there's a moment here? No, 0. So the only thing that I need is section 2. I want to recycle from the previous problem for the given load section 2. So the only thing that I need to do right now just to clarify. Look, this is like before the origin at this location, section 1. Before the origin at this location, section 2. Origin here, 3. I have put for this dummy, for the new for the new load in here, this load is 1 kip per foot. I have put section 1.1, the origin at the same location as the previous one. For section 2.2, I had the origin at the same location. And for section 3.3, I had the origin at the same location. And look, you already know this. Section 1.1, between 0 and 5, 8x times 0, gone. Section 2.2, between 0 and 10. This is the same as before. Remember, you had to take everything to the left of the section. This is the same equation as before. But now I have a new section 2.2 for the dummy load, 1/10, the reaction at A and X. These two needs to be assumed in the same direction, large M, and little m has to be assumed in the same direction. So in here, 1/10 times X, it gives you a minus 1/10 times X. I cannot revert to put an equilibrium because this means the same sign convention for the problem. The same as before. But now it's theta B. The rotation at B, summation of all the integration over the length, given load, dummy load, dx or di. We only have one section. 0 to 10, 4x minus 40, the same as before, times 1/10. So this is little m, dx or di. Theta B, 66.67. 66.67. Whenever it's a rotation, we multiply times 12 squared. A slope, or also called rotation, 12 squared. This was given inches to the 4, 29,000 KSI. This came in radians. It's very, very small. And the direction is given by the direction it came positive. We assume the moment clockwise, the 1 kip foot, it came clockwise. If you want to change it to angle, because we are used, we can tell the difference between 45 degrees and 90 degrees. So from radian to angle, it came a 0.353, very, very small. Any question? Any question about this method? So I know that we're going to continue on Wednesday, but I want to show you something. This is what I'm going to do on Wednesday. We had a frame, the deflection.
So whenever we take this free
simple.
body, we work with this free
Two
body
questions.
first. This
The
value
horizontal
that is going to be 0. That's going to be
deflection
0.
of point C.
That has to be
So
0.
point C, because of the
Internal
load,
forces, as
it's
you
going to
know,
try to move to the
we
right.
don't see it in here. Equal
or
and
to the
opposite.
left.
This has to be.
So this point is going to move. We want to compute the horizon. We also, a second question, the vertical, how much this one goes down or goes up. This is the dummy load to compute the vertical action. One at a time. The same that we did before. We had to take the deflection, the horizontal deflection first. And after that, the vertical deflection. So we cannot do both of them at the same time. But this is a very simple problem. We're going to work these problems and other problems. Now, I want you to know that I had office hours from 1 to 3 Mondays and Wednesdays. Today, I had 2 students that came for help. It worked out real well. But I know that some of you taking classes between 1 and 3. Some of you that had kids, you are teaching them because now you are the teacher in the schools are closed. So I know you're spending time teaching your kids or doing homework. It is not that easy to teach online. It's not that easy to be a student online. So this is a very, very difficult time. We're working together. We're trying to help you. So what I want you to know that let's say that you had class or you're busy during the day. If you need help at night, send me an email to my regular email. I will turn my virtual office on and I go over the problem in detail. Even in weekend, anytime that you need help, I will tell you if I'm in class or whatever. But this is the only way that we can survive. I need to help you and be bored. I fall to sleep, I had nothing to do, I cannot leave my house. So feel free to get in touch with me. We'll get the grader, the tutor. Please, just I'm here to help you. Just let me know. Any other question before we quit? Well, stay safe, healthy, and see you on Wednesday. Any questions in between, I'm here. Okay, bye-bye.